Struggling with math? You're in the right place. Welcome to Explaining Mathematics, the channel where we simplify tough problems, break down complex formulas, and turn confusion into clarity. From basics to advanced topics, we explain it all step by step. Let's start solving.
All right, take a look at this integral. It looks pretty intimidating, right? I mean, you've got this whole function raised to the fifth power, then it's multiplied by another function. Just trying to expand that thing out would be a total nightmare. But what if I told you there's a brilliant, kind of elegant shortcut to solve this whole thing in just a few simple steps? Well, that's what we're here to do. We're going to master one of the most powerful tools in your calculus toolkit, the substitution method. Seriously, this isn't just some random procedure to memorize. It's the key that unlocks integrals, like the one we just saw, that seem completely impossible at first glance. So here's our game plan. First, we'll dive into why this method actually works. Then, I'm going to give you a 5-step playbook you can use every single time. After that, we'll run through 3 different examples to really build up your skills, and we'll finish up with the key takeaways so you can master this technique for good.
So why does this amazing shortcut even work? Well, the best part about learning the substitution method is that you kind of already know half of it. It's just the chain rule from differentiation, but we're running it in reverse. At its core, substitution, or as you'll often hear it, use substitution, is really all about one thing: making our lives easier. We're going to find the messiest part of the integral, swap it out for a simple new variable u, and basically transform a hard problem into a super easy one.
This comparison right here tells the whole story. Remember with the chain rule on the left, when you take a derivative, you get that extra g prime of x term that pops out. Well, with substitution, we're looking for that exact structure, a function tucked inside another one, with its derivative sitting right next to it. When you spot that, that's your green light to simplify the whole thing into a nice clean integral of just f of u. Okay, so how do we actually do this? I'm going to give you a simple 5-step playbook. Think of it like a reliable recipe you can follow to solve any of these problems every single time.
Here's the process. Step 1, you choose u. That's almost always the inner function. Step 2, find its derivative, du. Step 3, and this is crucial, you rewrite the entire integral using only u and du. No x's allowed. Step 4, solve that new, way simpler integral. And finally, step 5, just substitute the original expression back in for u. We are going to follow these exact steps for every example.
All right, enough talk. Let's put the playbook into action. Our very first example is a perfect scenario where every single piece of the puzzle just fits together beautifully. And here it is again, the same integral from the beginning. Yeah, it still looks a little complicated, but we're about to see how our 5-step playbook just breaks it down into something incredibly simple. Let's get started with step 1. Step 1, choose u. The inner function is pretty clearly that 3x squared plus 2. Now, step 2, find du. The derivative is just 6x, so du is equal to 6x dx. And here is the magic moment. That 6x dx is literally sitting right there in our original problem, waiting for us. It is a perfect match. And this is the payoff. Our whole intimidating integral just collapses into integral u to the 5th du. I mean, come on, that's a problem we can solve in our sleep with the simple power rule. The integral is just u to the 6th over 6, plus our good old constant of integration, c. For our final step, we just have to swap u back out for what it actually is, the 3x squared plus 2. And there it is, our final answer. It's just a fantastic illustration of how a really complex problem becomes simple. No messy algebra required. Okay, so that first example was perfect, but let's be honest, problems aren't always so neat and tidy. What happens when the derivative we need is almost there, but it's off by a constant? Take a look at this problem. It has that same kind of structure, right? An inner function, 1 plus x squared, raised to a power. But let's see what happens when we go through our first couple of steps. So here's the catch. We set u to 1 plus x squared, so its derivative, du, is 2x dx. But if you look back at our problem, we only have x dx. We're missing that factor of 2. We are so close, but it's not an exact match. What do?
Well, the fix is actually simple, but it's really powerful. We can just introduce a factor of 2 inside the integral, right where we need it, as long as we balance it out by multiplying by 1/2 on the outside. Since 2 times 1/2 is just 1, we haven't actually changed the value of the problem at all. It's a perfectly legal move.
And look at the result. With that 1/2 just hanging out in front, our integral is now a perfect integral u to the 4th du. That integrates super easily to u to the 5th over 5. We combine that with the 1/2 that's already out front, substitute x back in, and we get our final answer. That one small adjustment made the entire problem solvable.
Okay, you're doing great. It's time to add one final layer to this: definite integrals. The process is almost exactly the same, but it includes one extra step that is absolutely crucial. And honestly, it's going to save you work in the end.
So here's our new problem: an integral from 0 to 2. The substitution part itself is pretty straightforward. If we let u equal x squared plus 1, then du is 2x dx, which is a perfect match. But the key question is, what on earth do we do about those limits, 0 and 2? Because those are x values, and we're about to enter the world of u.
Since we're changing our entire integral from the world of x into the world of u, we have to change our limits too. It's easy. We just plug our original x limits into our substitution formula. So when x is 0, u is 1. When x is 2, u becomes 5. These are our new limits of integration.
And this right here shows why changing the limits is so great. Our integral becomes a simple integral of u cubed du, and we evaluate it from our new limits of 1 to 5. We integrate, plug in the numbers, and we get our final clean answer, 156. And the best part? We never had to substitute x back in. Once we're in the world of u, we stay there.
Okay, so we've seen how the playbook works in 3 different scenarios. Now let's kind of zoom out and talk strategy. This is all about building that intuition, so you know exactly when to use this method and what common pitfalls to look out for.
You know, the key to really mastering this is just pattern recognition. This table here is like your quick reference guide. If you see a function inside another one, the inner function is probably your u. If you see a function and its derivative just kind of hanging out nearby, well, you've found your pair. With practice, spotting these patterns is going to become second nature.
And finally, let's talk about what to avoid. Think of these as checkpoints for your work. Forgetting to substitute back in, or, this is a big one, forgetting to change the limits in definite integrals are the most common mistakes. The best way to avoid them is just to be systematic. Run through your 5-step playbook and double-check this list every single time.
We started this with a problem that looked pretty much impossible, and we saw how we could turn it into something simple. You now have the playbook to do that yourself. So my final question to you is this: what challenging problems are sitting there in your textbook right now that you can finally unlock with this powerful method?
If this video helped you understand the topic better, don't forget to like, subscribe, and turn on notifications so you never miss a lesson. Comment below what topic you want explained next. Thank you for watching Explaining Mathematics. See you in the next problem.